When the CTF started, we looked at the challenges, and I already suspected, just because it's in style right now, that there could be an Ethereum smart contract challenge. And there was. Akoraida Monica. So I didn't even look at the rest and just decided to go for it. In the end, I didn't solve the challenge during the 2 days of CTF. So in this first video, I want to tell you about my failed attempts, and the second part will be about the crazy solution. Akoraida Monica. Weird name, but there is a reason to it. The description says, I exhausted all words, couldn't describe her beauty. So many handsome, charming men say that. That girl is Akoraida Monica. Her cute comes from her intelligence. She only admires who are smarter than her. So she designed this Q&A game and delegated someone to publish it on an Ethereum chain. Anyone who solves her puzzle could win 1 million Ether, and maybe her heart. Description: Web3 HTTP provider to access the private chain, which uses Geth, and the IP and port. The target contract has this address, the player account address is this. Query the source code for a specific contract can be done via this server, simply pass in the address of the contract. The goal is to drain the target contract, transfer all the Ether to your account, which means the balance of the player account should become at least 1 million Ether, and the balance of the target smart contract should become 0. If these conditions are achieved, the admin account will send the flag inside a transaction coming from this address sent to your player address. We can download some files, and they contain a Genesis JSON file, the player account private key, and the target contract's source code. And we must not scan the IPs and ports because that is not the challenge. Just to make this 100% clear, this is not 1 million real Ether, this is a private Ethereum chain just for you. The Genesis JSON defines the Genesis block of your private Ethereum network. Every blockchain starts with the Genesis block. In the downloaded files, you can find this Genesis block, and it contains the chain ID. Real Ethereum has chain ID 1, and this is the current mining difficulty, so 0. And the first Genesis block will also initialize several accounts with Ether. 19BA was our player address, so we already have a big number of Ether, but this of course is in Y, so converted to Ether, it's 200 Ether. The other account, 4927, is the admin account, and CF, I don't know. The other file we get is the Akoraida Monica game contract, which is deployed to address A9E6. But if you paid attention, you might have noticed that in the challenge description we get another contract hinted at here, 5E35, which when we open the site in the browser reveals a logger agent contract. A big issue already was that I didn't have Geth and Web3 installed to properly test and connect to the private network, and that alone cost over an hour. However, in the meantime, I did of course review the smart contract code. To do that, I use Remix, which is a very convenient IDE to test and develop smart contracts. When you add the game contract, you see that it expects exactly the Solidity compiler version 0425. So we have to select the compiler here. Each compiler is actually implemented in JavaScript, so it simply downloads that JS file. Loading, and now the contract is compiled. Akoraida Monica admires smart guys. She would like to pay 10,000 Ether to the one who could answer her question. Would it be you? A sample question, who is Akoraida Monica, and a sample answer with some weird characters, you beat me. And here is a logger address defined, 5E35, which is actually the logger agent contract we got earlier. So let's add that as well. Akoraida Monica is cute, so is her logger. Back to the game contract. The first code you will see is the constructor, and it already starts weird. This is inline assembly. Solidity is a programming language that is compiled to Ethereum bytecode, so it can run on the Ethereum virtual machine. Here I already knew, oh crap, this is going to be ugly. Especially because there is a jump, so this is redirecting code execution to somewhere else. I really didn't like that and not sure how to approach this properly yet. So I kinda ignored it at first. Next we have a modifier, only human. Modifiers are snippets of code that can be reused by multiple functions and usually implement access control. So this snippet is supposed to ensure that the address that is calling a function like the answer is on this contract is a human and not another contract. The check is implemented using a short inline assembly snippet using ext code size. So it checks the size of the code of the sender address. So if another smart contract, which would have code, would return here a value larger than 0, its code has a size. So then it would not be allowed. A human with just a regular Ethereum wallet would not have code. However, when I googled about that, just to be sure that's correct, I found the Stack Overflow answer, basically implementing the reverse, is this address a contract? But the comment down here was interesting. As far as I'm aware, this is the best method we have to check whether an address is a contract right now. But anyone using the solution should know that it's possible for a contract to return 0 from ext code size if the function call was made from within that contract's constructor. This means that you can't blindly use ext code size to prevent other contracts from interacting with yours. It must be used with caution. This was already a great hint. The constructor is very special and it's not a regular function. We will learn more about it later. And so at this point in time, the contract will soon be deployed, but it's not yet, thus doesn't have a code size. Other than that, we find 3 functions: start, new round, and the answer is. So for start, you can pass in a question and answer, but only if no answer hash has been set yet. Because it's set in here, this function can only be called once. The answer that is passed in is hashed with cashag 256 or SHA-3, and the current questioner is set to the address who called start. Next function, new round, can only be called by the current questioner and has to pay at least half an ether with the function call. New round takes a new question, but instead of an answer, has a string it takes as an answer hash directly, and then simply sets the new question and answer. It will also call functions on the logger, which appears to trigger events, so people can get informed that Acorida Monica has submitted a new question and a new answer. So start and new round appears to be functions that Monica or the admin would call, and we, the user, are probably meant to only interact by calling the answer is. This function is also payable and expects at least 1 ether to be sent there, and it makes sure that the hash of the answer submitted matches the current stored hash, which means the answer was correct. And in that case, we become the new questioner, and the balance, all the ether of this contract, is transferred to the person who answers the question correctly. And the logger is called to create an event to inform people of the winner. Okay, appears simple, right? We assume that the admin starts the game with a question answer, and if we can answer it, we will get all the ether of the contract. And on top of it, there is a small issue because the start method doesn't take a hash, but the actual string of the answer, which means the correct answer is publicly recorded on the blockchain, and we should be able to get it out of the transaction. So the attack plan was clear. We try to look up the transactions, extract the answer, then we submit the answer, and we win the challenge. The problem was though that the game server had issues and was often unavailable and down, so it was a bit annoying and difficult to play around with the challenge. But in the meantime, we could locally test this with Remix. So we can go to the Run tab and use the JavaScript VM, which implements a Ethereum virtual machine to debug the contract. Deploying requires a byte sequence as parameter for the constructor, but even if we enter one, the transaction execution will fail. It's probably failing because of the ugly jump in the constructor. So for a first testing round, I simply commented out the constructor code. Transaction mined and execution succeed. And now we have here a deployed Acorida Monica contract. And Remix is super cool because it now exposes all the functions that we can use to interact with the contract. Simple getter functions like version, sample question, sample answer, and so forth is also executed as a function on the contract, as you can see here. And now we can also try to call start, a question and an answer. And now that we execute start, we can query the question again, and now a question is set. Oh, and important is the fallback method. It's defined here and it's just empty. The fallback function is kind of like a default in a switch case statement. It actually is, but that goes already into the internals. But basically, if you try to call an unknown function on this contract, this will be executed instead. So we can use that to just send 10 ether to the contract. You can see now that our admin address has only 89 ether left, It had cost a bit to deploy and call those functions, and then 10 ether we just sent away. Now we pick another account and try to answer the question and see if we can transfer and win this ether. So we simply send 1 ether to answer the previously set question, but the transaction failed. VM error, revert. It was not successful. But we can click on debug and then step through the code to figure out why. And it all looks good until we reach the logger call, and here it fails. Which makes sense because we did not deploy a logger contract, especially not at this hard-coded address. And we can see in the bytecode execution that Solidity compiled code to check the code size of logger and then checks if the return was 0. So because there is no contract, it's 0 and the execution is reverted. But of course, with the real deployed contract on our private chain for the challenge, this should just work. So that's a possible attack we can try out if we find out the answer. So maybe it's time to look at the logger. The logger address is hard-coded here, and the game contract also defines the function for the logger contract here. But don't get fooled, because we know from the address, which we can use to get the source code, that the target logger contract is actually the logger agent. So how does this make sense that this game contract calls Accurada Monica wants to keep a log of the winner on a contract that doesn't even define that function? The magic lies in the fallback function again. Like I just explained, the fallback will be executed when you try to call a function that doesn't exist on the contract, and in there we find a call to delegate forward, which takes an address, which it gets from a call to implementation, and in there we find more assembly. Now this assembly is a bit easier to understand because there are no weird jumps, it's just a delegate call. It's a very typical smart contract pattern, and it basically turns the logger agent into a proxy contract. Essentially, this delegate call just forwards the function call that was received to the address here, implementation. Because you cannot change smart contract code once deployed, this allows a developer to always change the address of the implementation, and the proxy contract will always forward it there. So if somebody wants to change the logger, just deploy a new logger and then change the address via this upgrade function call. This means the logger agent, the proxy contract, will always have the same address, but which code is actually executed can be changed. And the actual logger that is called is just this here. It has some events. Let's look at it a bit more closely. So the constructor is a bit more normal. It will simply set the owner to the address of the person who deploys it. And here's a modifier for access control again, which checks that the caller is the owner. So these functions to change the owner with set owner or to upgrade the contract and set a new implementation address can only be done by the owner. That looks safe. However, the way how the storage is implemented here is super weird. It uses assembly storage store and storage load to handle the owner and contract address. The storage in Ethereum is a simple key value store. So here it loads a key and there it stores a new value for a given key. And so I thought it was super suspicious that the owner and logger contract was handled through that instead of just letting Solidity and the compiler manage that. So I thought that must be part of the solution. On top of that, I stumbled over another weirdness by accident. When Solidity compiles a contract for the Ethereum VM, you have to keep in mind that, like any VM or CPU, code execution starts at the program counter or instruction pointer 0. So there is no concept of a function, it's just assembly bytecode being executed. So in order to have functions to call, the Solidity compiler actually creates a big switch case statement for all functions. This switch case statement actually works with function signatures. The signature is 4 bytes taken from the cachec hash of the function, including the parameters. And hashes are pretty unique and that would be fine, but Solidity only uses 4 bytes of it. So there can be a collision. And it turns out that the logger function, Accurada Monica, wants to keep a log of the winner with the signature 0900F010 is exactly the same as the signature of the logger agent's update functions 0900F010. This means when the game contract tries to call Accurada Monica wants to keep a log of the winner, which is called on the logger agent, instead of going into the fallback method and then the delegate call and thus forwarding the call to the actual logger, the upgrade function is executed. Because that function will have the matching signature. And this is not a coincidence. These collisions don't really happen accidentally. The name Accurider Monica is so weird because the challenge author probably brute forced names until this logger function had the same signature. This must be on purpose. Now in the meantime, the challenge network was available again, so I wrote a small block and transaction logger in Node using Web3. So here I simply start by getting the first block of the blockchain and enumerate over the transactions attached to this block, and dump the transaction itself and the result, the receipt. And then I recursively call getBlock to get the next block. Now I know this code is ugly because I don't understand JavaScript and promises and asynchronous calls and stuff, so I know, you don't have to tell me. But it worked for me in the moment. Here's the output that I got. The first transaction deployed the logger agent. You can see that because in the receipt it has the logger agent address. This input of the transaction is the code that deploys the contract. The next one is the logger contract itself. Again, we know that from the receipt that contains the deployed contract address, and we were able to use it to retrieve the code of it with the browser. The third call is another contract creation of the game contract. It had a huge input, but again, resulting contract address is the known game contract. Oh, and in all these calls you can see that the from address is from the known admin account, and the to address for contract deployments, so where the transaction is sent to, it is null. The next transaction was actually sent from the admin to 5e35, which is the logger agent. So this is a contract function call, and do you recognize these bytes in the input? This is the upgrade method, and the parameter for it is this address. And this address was, what we just learned, the regular logger contract. So this is setting the implementation address for the logger where it actually delegates the call to. The next transaction was weird. It was another contract creation because the to field was null. The resulting contract F71C was new to me. But we could also get this code via the browser API. So this A and B contract simply calls start on the game contract. Super weird. And the next contract is from the admin to the game contract. So another function call using this function signature. And when we just decode this hex to raw bytes, we can see there are ASCII strings in there. A question: in Madagascar, you cannot take a picture of a lemur with gray hair. Why? You need a camera instead of gray hair. So this looks like the question and answer that is used for the game contract. And the admin also sent along a lot of ether with this call, the value here. So this is the ether we are supposed to steal from the game contract. But anyway, this means we should have everything to solve the challenge now, right? We simply call the answer is with this answer, and we should get the ether transferred to us, right? We can check if it worked by using the Web3 API with getBalance to check the Ethereum balance of the contract and our own game account. Wrote a bit more code to do that, but when I tried it, something was weird. I didn't get the ether. We just lost our 1 ether we had to send for the game contract. What? The code is clear here. We should get the money. Did I answer the question wrong? While this video is pretty short and sounds straightforward, this was roughly my state of knowledge after the first maybe 10 to 12 hours of concentrated work. So at this point the CTF area was closed for the day and I didn't have access to the private network anymore to work more with the Web3 API. We were back in the hotel and continued working on challenges in one of our rooms. So overnight and early next morning, I kept chasing down possible other attacks regarding the function collisions, the weird storage methods, and if I could somehow confuse owner and implementation, if the delicate call of the logger agent could somehow be abused, and so forth. A lot of different ideas. But I still kinda ignored the weird constructor. I was just scared or intimidated by it, and the rest was so fishy anyway that I thought the solution would be somewhere else. But at some point I accepted, shit, there's more to this challenge.